Good afternoon, Professor.
Good afternoon. Good afternoon.
Hi, Professor. Good afternoon.
Good afternoon, Caroline and Savannah. Thank you. And thank you for checking in. Thank you for thank you for both of you for clarifying. Or yes, good to see you. Hold on one second. Sorry. What happened? Yes, the other class did not. Yes. Okay. Hello. I'll explain this in a second. But yes, we're here. I just ran a minute late, and my board, of course, is late. But here. So wait, that was Caroline. That was Savannah. Good afternoon, Kevin. Hello, Douglas. Good afternoon, Erica. Good afternoon, Estrella. Good afternoon, Stephen. Good afternoon, Samaya. Hi, Euban. Good afternoon, Douglas. Good afternoon, Jose. Is that everybody? And Rashman. Good afternoon. Oh, he's coming. Oh, good afternoon, Irini. Sorry about that. Right. Good afternoon. I think that's already okay. And the board's coming. 1 second. I think the board's coming. Where's the board? Okay. Oh, and there's someone in the chat. The board. Oh, and someone's in the waiting room with Dinah. And who's that? Oh, did I say Irini? Sorry. Good afternoon, Irini. I guess I did. Okay. We're gonna start in a second. I want to get to yes, thank you for your patience, everybody. I started like a minute or two late today, and the board is coming. And yes, I didn't mean to create any confusion. It is true. Like a couple of you checked in right before class. It is true. Hello. It is true that just like about 3 weeks ago, you guys, we didn't meet, whatever that day, that Monday was a Tuesday or Tuesday was a Monday. This section did not meet, and I asked all you guys to watch the video from the other section, for points and call that class. But I really was very impressed with many of you that gave me a summary of the video that you watched from the other class. It really actually was quite an impressive summary. In most cases, almost any case where someone did do a summary, I really was actually quite impressed and happy. It goes to show, and Lord knows, maybe for some of you, there was a better way to learn. I don't know. But so today is the switch. Today, the other, just to be clear, if you heard from your friends or something there was no class, it's true. The other section, they didn't have class today. They're going to watch this video, your video, and ideally that's keeping things even. Stephen, we're all having the same amount of exact instruction time, hopefully, or anyway, you get the point. But right, we do have class today. The other class did not. And we're going to get rolling right now. I want to... Okay. I want, right where we ended on Monday, we ended with this discussion of omega, right? I mean, Monday was a big, if I'm remembering correctly, and again, stop me if I'm wrong. Oh, and someone might want to remind me too. I just remember I did not put in a game turn yet for tonight. Often I can rely on Caroline to, but you might want, hopefully at some minute in the middle of class, I'll remember to do that. Maybe remind me if I don't. In fact, I think, okay, anyway. So 2 days ago, I spent a long amount of time trying to re-establish for everybody what a radian is so that we can ultimately understand what it would mean to measure an angular frequency in radians per second, right? That well, I'm going to start. Hold on. right? Okay, what I got on this whole thing about radians and radians per second and all of this stuff because we were guessing, we were conjecturing a possible, well, we were building up a conjecture for an expression that we were hoping could possibly be a solution to the differential equation written at the bottom of this page, right? The differential equation is the differential equation that describes this oscillation of a mass on a Hooke's law spring, right? That differential equation describes all the basic physics facts we know about a mass going back and forth on a spring. But what we want is to be able to unpack or solve that differential equation and get an actual position function. We want, and I know I keep saying it, but I don't think I can say it enough. That equation at the bottom of this sheet, that differential equation is not an answer really to anything. It's really something that's posing a question. It's a description of the physics. It's a bunch of information, but the information is packed in so tightly, it's not accessible in that form. The information that we're looking for, just to remind you, we're looking for X as a function of T. We're looking for a rule, a relation where you plug in time as the input, as the independent variable, and it spits out position X as the output, right? So we're trying to solve that differential equation. And the way we're doing it is by a sophisticated version of guess and check. And it turns out many differential equations that is the only method available. So we spent all this, like the last 2 days, building up our reasons for why we're going to guess that our solution to the harmonic oscillator, our position function, for this oscillator, we're guessing it looks something like x equals x naught cosine of omega t. And omega, we've just introduced into our lives. Like I want to emphasize that too. I mean, I know you've been dealing with it in lab, and I know labs are getting more and more sophisticated. But I'm saying like this omega here, I mean, it looks like a W, but it's an omega. That omega is not meant to refer to something that we've already established earlier in physics or that you were supposed to have memorized or know from the web. We're making it up right now, right? Remember, what we're saying is there's got to be some constant term in our guess. If our guess is right at all, based on units alone, there would have to be a constant next to the t that would be measured in radians per second. And therefore, since it's some number, some measurement of radians per second, it's got to be a measurement of some rate at which this system is passing through radians every second. We're going to call that angular frequency because it's the frequency, how often the system is passing through angles measured in radians. But the system is a mass going back and forth on a horizontal axis. So the purpose of all of yesterday was to try to bridge the gap of saying, wait, what? If we're talking about something going straight back and forth on a horizontal axis, what does it mean to talk about the frequency at which it passes through radians of angles? Like, where are angles and where are radians in all of this? And the ultimate punchline of all of what we were saying yesterday, the ultimate punchline, and I really ask you to keep going over it or make it, the ultimate punchline is a radian is a sixth of a cycle. Like, again, let me say that again. Please write, it's approximate. It's not exact. It's a little bit less than a sixth of a cycle. But what a radian is a portion of a cycle, approximately a sixth of a cycle. Where did I get a sixth? What I'm really saying is it's a 2/π of a cycle. What I'm really saying is if a cycle is a size of 2π radians. 2π radians equals one cycle, like exactly. Therefore, 1 radian is a 2/π of a cycle. 2π is approximately 6, right? So omega, what omega means, the whole development of yesterday, of Monday, is that what this omega term would mean, should mean, is the rate at which our mass is cycling back and forth, back and forth, back and forth. It's the rate at which the mass is cycling back and forth, but it's just measuring the rate in a funny way. It's measuring every sixth of a cycle instead of every full cycle. If you want to know literally how many cycles per second the mass is doing, you divide omega by 2 pi. Like, all right, I'll say that again. Yeah, I'm going to summarize again. We wrote this down Monday, but just to get to be clear, like in other words, like regular frequency, standard frequency measured in cycles per second, or in other words, measured in hertz, is the angular frequency divided by 2 pi, right? And period is 1 over standard frequency. That's a summary of everything we were saying yesterday. But again, and I believe it was it this class? I believe it was, yes, someone in the direct chat in this class asked me, like, why do you have, yeah, it totally was this class. Yeah, because you guys were, oh, that's right. And you guys even did the practice problems. That's right. I'm sorry. You did the problem. So, and other class who's watching this video right now, you might want to do some practice problems. Look at the updated PDF of the notes. It has practice problems in them. Because this class that I'm talking to you right now asked a really good question and you guys didn't. Okay. So the summary is that there's 3, just to remind you of what we said on Monday, there are 3 distinct but utterly interchangeable, utterly relatable, mutually relatable ways to describe the rate at which an oscillator cycles. The 3 ways are angular frequency, standard frequency, and period. Angular frequency is radians per second. Standard frequency is, angular frequency is radians per second. Standard frequency is cycles per second, also known as hertz. And period is seconds per cycle, also known as seconds. If you know one, you automatically know the other 2. If you know one, you can automatically figure out the other 2. If you can picture or understand one, you should get used to translating that understanding to understand the other 2. And as a person in direct chat asked yesterday, like, why do we have more than one of these? Because angular frequency is the most mathematically powerful and direct. It allows us to do cosines and plug into these expressions that we're developing. And period is the most experimentally measurable and therefore the easiest to picture. Standard frequency is the bridge between the 2. Okay, that's the sum. So all of this talk on Monday was all about, like, what does angular frequency mean? What do radians mean in the context of an oscillator? All that. Okay, so that was all to justify or to enhance our understanding of this omega term in the cosine function. But remember, the cosine function is our guess, our conjecture. We're guessing that it solves d2x dt squared equals negative k over mx. So what what homework 2, the math methods thing, it gives you a series of exercises at the beginning to help you practice this idea of checking a guess in order to see whether it works or not, whether this is or is not a solution to the differential equation. Right now, it's just a guess. We haven't proven that it's right. We've just argued that it's a good guess. To prove that it's right, to check, I'm going to do now what we did last week. Hold on, let me just turn on. What? Wait, okay, hold on a second. I'm just turning my phone off to focus. How do you do that again? So focus. Do not disturb. Yes. Okay. Does that ever work? Does that actually work? We'll see. Okay. And if so, is there a button like that on my 8-year-old? Okay. So we're going to test. So I'm now going to test it. It's going to be very similar to what we did 2 days ago with a very, very similar guess. And what I'm about to do is not just similar to, but is identical to what you're being asked to do in the first few exercises in homework 2 in a fact, I am about to answer the first two exercises in homework 2 different. Let's test this conjecture by differentiating. So this is simple, but we haven't exactly done, so bear with me though. Hopefully this is practice and review for some of you. It's going to look similar to something we just did a couple days ago with the chain rule and all that, but I'm also going to show you something new with it now. So we're going to test this guess to see whether it's really right or not. And remember, what we're guessing that if you want to know where a mass is at any given point in time, a mass that's oscillating back and forth on a spring, we're guessing that where it is at any given point in time is a cosine function of time with an amplitude defined by its initial displacement and with an angular frequency, with a rate of going back and forth defined by that omega term. That's what we're guessing. Now let's see if we're right. Well, the first derivative, so we're guessing this. That's our guess, right? So the first derivative, actually, do we have to, should I do this? Should I? Yeah, I'm going to pause for a second. I'm going to ask you, we've done it before, sort of, but just in the direct chat, please. I'm going to ask you, what is the first derivative? Tell me in the direct chat, please. Tell me dx dt, assuming that x is x naught cosine omega t. In other words, t is the independent variable, like t is the variable, x is the dependent variable. Everything else in there, the x naught and the omega, they're just constants. They're like numbers. So I would like, in the direct chat, I'm going to wait till I get 3 answers in the direct chat, right or wrong. I want to know the first derivative of that expression. I want to know dx dt if x equals x naught cosine omega t. Okay, again, x naught is a constant, and maybe in the homework it's called a, same thing, capital A, x naught, same thing. But I'm going to wait until I get 3 answers in the direct chat. Like, what is the derivative with respect to t of x if x is equal to x naught cosine omega t? That is the question. I'm going to wait until I get 3 answers in the direct chat. Oh my God. Or at least wait. I'm gonna, oh, cool. Okay, that's one answer. Okay, wait. So cool. Okay. I might even respond. Okay. Awesome. I see 2 answers. That's awesome. I'm impressed with both of you. If you are in the chat, I'm impressed with you. Hold on. Awesome. Awesome. I have 2 answers that are very well. Now I have 3 answers. Okay. Awesome. All right, I'm just going to respond, actually. Hold on. I mean, you guys can keep going if you want, as long as I'm answering it. I'm impressed with all of you that just put something in, and you should definitely submit for points, blah, blah, blah. Where to go? Okay. Awesome. Oh. Awesome. Okay, these are great. As soon as this is a race now for group. Okay. Awesome. So I just got a lot of answers in the direct chat, and ultimately, I think every single one of them was actually either darn close or right. All right, awesome. Yes. So what a lot of people are, that's great. Thank you guys. What a lot of people are telling me in the chat, I'm just going to recopy it. So if we're saying x equals x naught cosine omega t. Now, just to be clear, off in the margin, so sometimes I use x naught. Oh, cool. Okay, sweet, direct chat person. Sometimes I use x naught. Sometimes I use a. physicists, just to be clear again, x naught technically means value of x when t equals 0, right? X naught technically means the very first displacement. Capital A technically means the maximum displacement, which we know is amplitude. Okay, but for an oscillator like this, assuming energy is conserved, assuming the thing starts from rest, the maximum it ever gets is the same thing as its initial displacement. So we tend to use the two terms interchangeably. We use one when we're emphasizing that it's the first place, and we use the other when we're emphasizing that it's the biggest place. But yeah, they mean the same thing. But as a caution, when it comes to exams or life or other courses and stuff, you always want to write your answers in terms of whatever was actually given in the question, if you know what I mean. I'm just talking to all of you, like, just be careful of it. So anyway, if this was the function, I agree with what everybody put in the chat, that the first derivative of it, well, this is a function of a function, right? The outer function is x naught cosine. So the derivative of the outer function is negative x naught sine, right? But then you have to do chain rule. So you have to multiply the whole thing by the derivative of the function on the inside, right? And the function on the inside is omega t, right? We're doing x naught cosine of omega t. So the derivative of the inside is omega. So we multiply the whole thing by omega, and then we just rearrange to make it a little bit prettier, and we say like this. Okay, so that's the first derivative, right? And now now we're going to do, excuse me, now we're going to do the second derivative. And I'm going to ask you again in the chat. Hello guys, welcome back. Great to see you. Wow. Okay, he's got a friend, so he is focused. Okay, it's a girl. Oh, okay. So in the direct chat, could you please, maybe this will be a little, do the second derivative. Oh, and in fact, I noticed this in the homework. Yeah, some of you were able to do first derivatives, but not second, which is a little bit curious. So try the second derivative now. Just do the same exact thing you just did, but on this function. Now take the derivative of this, and I'll wait for. I won't respond directly this time. I don't think. Well, maybe I will. Oh, wow, that was fast. That was fast. Oh, that's awesome. I love this class. Okay. Oh, awesome. That was so far. I'm not going to. So far, everything I see. Well, again, be careful of whether it's A or X naught. I mean, just. Like here we're using X naught, but yes, okay. But yes, awesome. Everything I see in the chat so far is right. I'm psyched. I'm waiting for one more in the chat because. So I'm going to wait for one. But just, yeah, and we all understand too. I'm going to wait for one more in the chat before I go on. But I'm going to say to everybody, let me know in private if ever you're confused. Please know X is a variable, right? It's the dependent variable, but X naught is not a variable. It's a constant, right? X naught is the particular unchanging value of X at specifically the moment that t equals 0. So X naught is a constant, which we sometimes use the letter A, but X is a variable, just to be clear, because I know it's hard to write in the chat with the. But you want to, okay, I'm going to wait for one more in the chat. One more. I want the derivative. Well, I guess people aren't. All right. I want the second derivative. I want the derivative of the derivative. So I'm going to wait for one more person to make me feel like this is a class. But the two people that are in the chat right now, I totally agree. I mean, one of you, just be careful of your A or your X naught, whatever I'm writing the question. But yes, I totally agree. In fact, actually, the other of you, in the direct chat, you wrote X. I assume you mean X naught, just like the person who wrote A. I assume you mean X naught, but just be careful. But I'm going to wait for one more person. Oh, there we go. Okay, cool. Thank you, direct chat person. Okay, but I'm going to wait for one more person. Like this, let's all get our tuition money here. I want the derivative, or write in the chat, you've lost me, or I can't do it, or you're talking too fast. I don't know what the question is, but give me something. I've got two people in the direct chat who have answered this. That's great. They're now going to be elected president and prime minister. There's another thing in the chat. Yes, sweet, awesome. That is awesome. Okay, all right. So I just got two things. Interesting person who just. All right. No, it's not. Well, okay. I'm going to say the answer next. This next derivative I think some of us might think, I think more than one person in the room from experience and from being smart is thinking that this might go to zero, because that does happen with some things, some functions like 1/2 AT squared. Once you take a couple of derivatives, you get to the answer 0. With like power functions, that happens. But this function will always have derivatives. The derivative of cosine is negative sine, but the derivative of negative sine, well, the derivative of sine is cosine. So put another way, the derivative of negative sine is negative cosine. Like this thing does have a derivative. It's not 0. I mean, I'm saying with all due, but by the way, that's total points for, that's another portal. You can put that in. I'm going to say, if we do the derivative of this, we're going to do chain rule. We're going to get negative omega x naught cosine omega t, like the derivative of sine becomes cosine, but then the chain rule brings the omega out again. So we have another omega times the whole thing. So it's negative omega squared x naught omega t. And let me know. Oh, good. I see another person in the chat with that. 1 second. So I think the second derivative is this. Now remember, the question is, so I haven't proved anything yet. Oh, good. All right, awesome direct chat person. Awesome. Okay. Now, I'm not done. I've taken 2 derivatives. That's an undertaking for some of us. Like, okay, I've taken 2 derivatives. That's nice. But the whole reason I've taken 2 derivatives is I'm trying to see. I've taken 2 derivatives of this particular function to see for this particular expression for x in order to see whether when I take 2 derivatives, do I satisfy this equation? In other words, I've taken 2 derivatives in order to see whether I do in fact get negative k over m x. Oh, wait, let me look in the chat. Oh, wait, that's an interesting question in the direct chat. Hold on, let me just make sure I understand. Okay. Hang on. All right. So there's a question in the direct chat. So at least let me first of all say, at least 2 of the people who are in fact speaking and communicating in the class today, at least 2 of them are asking good questions or raising possibilities of what. More things are happening in the chat. Just hold on a second. Oh, okay. One sec. Okay, look, at least 2 people of the people who are actually talking are raising legitimate concerns about why or why not are we getting 0 if we take, or under what conditions would we get 0 if we take a derivative. Now that's at least 2 people of the people who are talking. So I have to believe that they're not alone and they're not crazy. Like that means there's other people in the room. Like if you're paying attention at all, but you're not talking, like it seems like a legitimate concern. Like I'm glad that people have the guts to bring these things up. Like at least 2 people of the people talking seem to be wondering about, hold on, like why is this thing not going to 0? Or when would a derivative go to 0? And one person, for example, is saying, well, is it because of that x naught term there? Is it the x naught term that's preventing the second derivative from being equal to 0? Now, that is a very probing question. My simple answer is no, it's not actually because of the x naught. Even if the x naught weren't there, I still don't think the derivative of this would be 0. But this is important enough question. Let me sidebar for a moment. Like, let me give you an example of a function that would go to 0. let's say dx dt equals if dx dt just equaled x naught omega, okay, if that were dx dt, then d2x dt squared, if that were the first derivative, then the second derivative would be 0. And here's why. Well, what I'm really getting at is, as long as there's a t, as long as there's an independent variable anywhere in the function's expression, then the derivative of that will not be 0. Like, what we get a derivative of 0 whenever we're taking the derivative of a constant. The derivative of a constant is always 0, and the derivative of nothing else is 0. So if they're, and a constant means letters or numbers that aren't the variable, that aren't t. So so I would like to hear from at least the one person in the direct chat. Like, I don't know if what I just wrote on the board actually addresses you or helps you, but what I'm saying is the x naught is a constant. It's there, it's doing something, but okay. I'm reading the chat. I'm really glad that people are hanging in with the chat here. Isn't it? Okay.
Yep. Sure thing. What's a nice question?
Oh, okay. So first of all, people in the direct chat, thank you very much for this whole question in the first place. Second of all, the people that asked, or at least one of the people that asked, totally now has said that things are clarified for them. So that totally counts as closing a conversational path. Like, that's points in itself, just for bringing this so that I can move on. I mean, but then, so this is great, but it also seems to be bringing other people into the discussion. Someone else in the discussion is now saying, great question. Is it because there's no value of x and then it is 0? If it's really because there's no value of t. If there's no value of t in the expression, then the derivative is 0. So, but the basic point that you're making in direct chat is, yeah, if there's no variable in the expression, if it's only constants, then the derivative is 0. Yes. So I think hopefully this is making some sense to people. I'm not sure, but okay. So I'm going to go on. So this is what we have so far is, am I about to lose the board? Yep, I knew it. Oh, here we go. Okay, so now we still have not completed our test. We have the test. The question is, when we took the set, remember, we're testing an expression to see if it satisfies a condition. The condition is, when we take the second derivative of this expression, do we get back itself times negative k over m, right? That's what the differential equation says, that the second derivative with respect to time of x equals negative k over m times x. So we just built an x, we just took two derivatives of it. The question is, did the thing work or not? Well, our second derivative seemed, I'm just going to remind you again, the conjecture was that x equals x naught cosine of omega t. That was the conjecture. The second derivative yielded negative omega squared x naught cosine omega t. I have to tell you, the reason I do this so many times, and the reason I'm doing it slowly, is the first 100 times that I saw this, when I was a student or whatever, first 100 times I looked at this and I was like, okay, whatever. I don't know. It's gobbledygook. I don't know what I'm supposed to do from here. Like, how do I know? I just looked, it just says the second derivative equals negative omega squared x naught cosine omega t. I don't know what that tells me. I know that I just took two derivatives, but so what? But the big so what it's always easy to see when someone else shows you, but it's hard to see on your own which is why you want to practice this. The big so what is that that this whole piece right here, x naught cosine omega t, that is x, right? That's what we're conjecturing x to be. So therefore, you got to remember that's the key step easy to forget that is x, supposedly. X naught cosine omega t is what we mean by x. Therefore, apparently, d2x dt squared does equal negative omega squared x. Wait a minute, and that's looking good now. In other words, when we took the second derivative of x with respect to time, we got back x itself times a constant times -1. And that's pretty much what was supposed to happen. Pretty much what we wanted to happen. But the good news is it's what we wanted to happen. The bad news is I'm saying pretty much. Why am I saying pretty much? Because we wanted d2x dt squared to equal negative this constant times x, right? So, negative, right? Our original differential equation was d2x dt squared equals negative k over mx. We guessed a certain x. We tested it out, and we found out that the certain x that we guessed yielded negative times a constant times x. But apparently it was a different constant. Or was it? Wah, wah. Boom, 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 boom. What I'm saying is this. Remember that omega squared was a placeholder, or excuse me, omega was a Greek letter that we just put there that we said had to have units of radians per second. We put there because it had to be there because it had to have the right units. And then I went on this big romp and frolic to describe what radians per second could possibly mean and what it could mean that there's a radian there, that there's an omega there, blah, blah, blah. But we never knew what the number was. We just knew, and we just made up a name for a number that we thought had to be there. K over M is a number that has to be there. So it looks like what we're saying is, we're actually saying a bunch. We're saying thus, x equals x naught cosine omega t evidently does work. It does satisfy the differential equation as long as omega squared is just another name for the same constant as k over m, right? Like when we differentiated this thing twice, we got this. So as long as this, like both time, either way, it's negative times a constant times x. So as long as omega squared and k over m are just two different names for the same number, then we're good and we did solve it. And there's no reason why they can't be. I mean, we could call a number anything we want. In other words, this omega solution is a solution as long as by omega we mean, well, here, I'll write on the next page. So now I'm saying something slightly new, okay? Like if it feels to you like we're sort of doing the same thing every day for like 3 days, but with the details being just different enough to be a little bit confusing, you're right. I mean, we're not on purpose trying to be confusing, but for the last 3 days, we've been sort of building up and playing with this cosine solution and then testing it and showing that the cosine solution is a solution to the oscillation differential equation. But like one day we used K over M and one day we used omega, and we're sort of like doing it from different. What I'm trying to say today, I'm trying to put the pieces together and say the bottom line is this. If Hooke's law governs a spring, if a mass is going back and forth on a Hooke's law spring, then the differential equation that describes it is d2x dt squared equals negative k over mx. And the solution to that differential equation, like our ability to predict where the mass on the spring is at any given moment, is x equals x naught cosine omega t, for which omega actually must equal square root of k over m. So on the one hand, I'm just saying mathematically, omega is one name for a number measured in radians per second, and square root of k over m is another name for the same number. Mathematically, I'm saying there are two different names for the same thing. But physically, then, if all of this is true, if we're saying x equals x naught cosine omega t and omega equals square root of k over m, or in other words, if we're saying what we said on the first day when we just tried to, if we're saying x equals x naught cosine of square root of m times t, then what we're ultimately saying is the rate we're saying that omega thing that we just put in there to mean rate of cycling, we're saying that we just discovered what determines that rate. By solving the differential equation, we actually found out not only a position, we found out that it'll go back and forth according to a cosine function, and the rate at which it will go back and forth, we can call omega. We can call that rate, that angular frequency omega, but it turns out we just discovered in the process of checking our solution that omega is fully predictable or fully determinable by the square root of stiffness over mass. That's a discovery. I'm saying, if anything, like, you can memorize that if you want. That's a takeaway. That's on the interwebs. Omega equals square root of k over m is something we've just discovered right now by doing the differential equation. Yeah, let me go. Okay. Now I want to back up and show you something or explain something. You know, we're really increasingly getting rid of numbers from these equations, right? We're using letters to stand for numbers, but there's different types of letters, right? There's variables and there's constants. Within variables, there's two types. There's independent variables and dependent variables. I want to write T as independent variable and X as a dependent variable in this context. I want to bring to your attention now that within constants, there's different types of constants as well. I mean, first of all, there's something called a natural or universal constant, right? Like Planck's constant or like big G, the universal gravitational constant. I mean, those don't come into this, but you know, there's such things as constants that are just constants everywhere through the universe. Then within a situation like this, where you set up a system or an experiment in the lab, numbers can be constant for different reasons within a system, within an experimental setup. So X naught or A, which is really the same thing, those are constants, right? And they are constants of what we would call condition or configuration. X naught is an initial condition. It's where the mass is initially. X naught, and therefore A, X naught remains X naught throughout an entire problem, but it indicates how you decided to set up or configure the ingredients, the equipment of your experimental design, right? X naught is how you set up the mass on the spring. It is a choice, and all lab groups could be given the same equipment, but one lab group might set up the equipment to an X naught of 0.15 meters, and another lab group might set up the lab equipment to an X naught of 0.30 meters, right? But there's a different type of constant called a parameter. K and M are parameters. A parameter is what it says, is a constant material property of the system. A parameter is like a feature or characteristic of the ingredients in your experimental design. And once those ingredients are picked, it doesn't matter how you set them up, the parameters don't change, right? So like mass and spring, I don't care what you do with it. Your spring has a certain stiffness, your mass has a certain heaviness. If those are the same as your lab group, as the next lab group, then they're the same, and it doesn't matter what you do with them. Why am I bringing this up? Good question. Right? So just note that the first thing I'm saying is, in this context of a mass oscillating on a spring, the angular frequency is entirely determined by parameters as opposed to conditions, right? I'm saying so far that the rate at which this mass goes back and forth is fully determined by how heavy the mass is and how strong the spring is. It's not at all determined by how you set up the mass on the spring. It doesn't matter how far back you pull the mass initially. Apparently, it's going to make the same number of cycles per every second. And why do I say apparently? Because I don't see any X naught term in the omega expression. right? Omega is based on K somehow, and it's based on M somehow, but it doesn't seem to be based in any way on X naught. Omega is independent of X naught. It is determined by parameters, not by conditions. That's the first thing I'm saying, okay? The second thing I'm saying, so as opposed to conditions. To put it in broader terms now, what I'm saying is, so for this type of oscillation, what do I mean by this type of oscillation? I mean oscillation that can be described this way. And therefore, this way. For this type of oscillation, it seems that frequency is independent of amplitude, right? It's just another way of saying what I said a moment ago, but I'm saying the rate at which this thing goes back and forth doesn't seem to have anything to do with how far back and forth we asked it to go. Now I'm going to get very excited about it. If I'm not careful, I can get very excited about that idea, and I will. Whether you find it exciting or not, hear the idea again. Frequency, like rate of cycling in time, seems to be utterly independent of size of cycles in space. How fast this thing is going back and forth doesn't seem to have anything to do with how big of a space we ask it to traverse. This type of oscillation, okay. The frequency is that constant. Oh, I should even say frequency constant. The frequency is that constant. It's not just so we have an oscillation here. Oscillation means cyclical repeated motion. Something's happening frequently. Well, first of all, the frequency here seems to be some kind of constant. But second of all, the constant is so constant that it doesn't even seem to be affected by size of cycle in space. This type of oscillation where this occurs, where the frequency is independent of amplitude, this type of oscillation is called simple harmonic oscillation. I know we've probably already been using that word for weeks, especially in the lab, but I want to now be explicit. Oscillation is anything going back and forth cyclically in any way, spastically or not. But when something is going back and forth so regularly, so constantly, that the constant rate at which it goes back and forth isn't even determined by the amount of space through which it's going back and forth, then that's called harmonic oscillation. Harmonic oscillation is any oscillation that is describable by this differential equation and has this property, that the frequency is independent of amplitude. Now, say it one last time, then I'm going to go on. Like we are saying, I mean, this is actually a really, really big, I have to be so careful like this because anytime I always try to not make a big deal out of this. And then the minute I start talking about it at all, I go bananas for like day, because it's such a big deal. I mean, so bear with me for a second. So I'll try to be quick about this, but like, it's such a surprise. It's so weird. And the implications are so wide. Like we're saying, we take this mass on the spring, we pull it back here to 15 centimeters, we let it go, and it goes wah, 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 and say each wah, wah takes whatever we figured out, 2 seconds, let's say. So we pull out to 15 centimeters, it goes 2 seconds, like 1 Mississippi, 2 Mississippi, I always do this wrong, like 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, right? It's taking 2 seconds to do every cycle. But if all the math that we just did is true, if you're really following what I'm saying, that the frequency is independent of amplitude, then what that means is if we start the whole thing again, we have that same mass on the same spring, but we have the same equipment, but we're a different lab group. So we start all over again, and instead of pulling it out to 15 centimeters, we ask the thing to do like 75 centimeters. We ask it to go like, wah, wah, right? Evidently, that group is also going to get 1 Mississippi, 2 Mississippi, like 2 lab groups with the same equipment. We're saying if one lab group just asks for small oscillations, and the other lab group asks for big oscillations, evidently both lab groups are going to get, I mean, within reason, the same amount of time. And then if this lab group over here just wants these tiny, like 1 millimeter, like ring, ring, apparently that's going to go, Mississippi, Mississippi. We're saying no matter how much space we ask the thing to travel for each cycle, it's somehow going to manage to do it in the exact same amount of time as all of its neighbors who are doing different amounts of space. That's a really surprising thing to say. Like, to be really concrete, what I must be saying, I'm saying that that a mass, that if all of the things are the same, if it's the same stiffness of spring and it's the same mass of mass, then we're saying whether you do 30 centimeters cycles, you'll do it in 2 seconds, or if you do 75 centimeters, you'll do it in 2 seconds, or if you do 3 millimeters, you'll do it in 2 seconds, right? So we're saying, if we're saying that the really long, far oscillation cycles are being done in the same amount of time as the really short isolation cycles, then we must be saying that the really far ones are going much faster than the really small ones. Evidently, a mass on a spring will go really fast if it does a long oscillation, and it'll go really slow if it's doing a short oscillation, and it'll adjust its speeds perfectly so that it all works out always to be the same time. Let me put it another way. We're saying if you believe that omega equals square root of k over m, which is what we just argued, if omega equals square root of k over m, or put another way, t equals 2 pi times the square root of m over k, all the same. If you know that, you could just figure that out from just k and m. That means before you even set the thing up, no matter where you put the mass, it's going to take the same amount of time to go back and forth. It's going to take the same amount of time to do a cycle in time, regardless of what space it undergoes. What is that? Anything. So it's measuring time irrespective of space. What we have a word for anything that can do that. We have a word for any device that can keep time regularly irrespective of space. That word is clock. A harmonic oscillator is the fundamental ingredient to any clock. Anything that keeps time, anything that is a clock, is at core a harmonic oscillator. Whether it's on the mats on little springs going back and forth in like a wristwatch, or a pendulum going back and forth in a grandfather clock, or an like a resistor capacitor electronic circuit in a digital watch, or whatever, anything that's keeping time is fundamentally at core a harmonic oscillator. To oscillate harmonically is to keep time. Okay, I could go on and on. I mean, and you might even be saying, well, I don't know what you're thinking at this point, but you might be thinking like, when's lunch? And the answer is, I think we're up to dinner. But you might be thinking, one thing that could be a thought right now is, okay, this is more like idealized physics and more idealized math and like, yeah, at the same time, but like, come on, in the real world, we know, like, if you were to make a pendulum, like, we know a realistic pendulum or a realistic mass on a spring, like it goes back and forth, but in a real world with friction and all that, it eventually like slows down and eventually stops. So really, how true is any of this? But if you're really hearing what I'm saying, it really is something very powerful, even or especially about the real world. In the real world, of course, a mass on a spring does eventually slow down. And a pendulum eventually slows down. But if you really hear what I'm saying is that when the pendulum slows down, it actually slows down. So therefore, it doesn't slow down. Like what? I'm going to say that one more time. Wait, I'm actually going to do this. 1 second. We have 12 minutes. Yeah, we're on track. Hold on 1 second. You know, I'm being a jerk. Hold on. I'm going to say this one more time. I'm going to give a quick story about Galileo here if I can. So just raise your electronic hand if you are hearing me speak right now. Awesome. That's a lot. I even got a heart. Okay. Awesome. That 4 people, 5 people, 6. Okay. 6. Yeah, that's good. All right. Good enough for me. Thank you. So here's what I'm saying. Real world point. When an oscillator, a mass on a spring, in the real world, if you watch it like in the lab, of course, it doesn't really go on forever in the real world. And of course, it doesn't look like it makes the same swings forever. Like it goes like, it damps out. So it seems to slow down in the real world. But what I'm saying is, if you're really following me, I'm saying frequency is independent of amplitude. So even in the real world, when a mass on a spring when you look at it, you're like, oh, it's slowing down, it's running out. Oh, that's not really, we couldn't really use that as a really good clock or anything because like, it's not really keeping regular time. I mean, look at it, it's slowing down. No, if you look at a mass on a spring in the lab, or you look at a pendulum in the lab as it's slowing down, what I'm really saying is, what's happening is the swings are getting shorter and shorter in amplitude. In the real world, right? A pendulum, you let it go, there's friction in the real world, so the amplitude of the pendulum will decrease, so the swings will get shorter and shorter in distance. That is true. So watching it, your eye will be like, oh, look at that thing, it's slowing down. But in fact, while those swings are getting smaller and smaller in distance, what I'm arguing here is the pendulum literally is slowing down. It's got less and less speed each swing. It's got less and less speed, i.e., the bigger swings start off with more potential energy, which gets converted to more kinetic energy, right? So whether it's a mass on a spring or a pendulum bob or whatever, if it's a mass on a spring, when you started all the way out here, you started with a lot of potential energy. So it comes in, it's converting its potential energy to kinetic energy. So it gets to here, it has all this kinetic energy. So on average, the big swings have a lot of kinetic energy on average. They go fast. They literally do go faster on average than the small swings. So when you watch something visually and you see it damping down, and you're like, oh, that thing is slowing down. Well, the thing is, it literally is slowing down. Each one of those swings, those cycles in space, is actually slower in speed by apparently the exact right amount, so that each swing still takes the same amount of time. So even a realistic pendulum, when you watch it, and you're like, oh, look, that thing is slowing down. Well, it's slowing down in the velocity sense, and it's slowing down in the amplitude sense. But since it's doing both, in a way, 2 wrongs make a right. And in effect, in the end, if the early swings were like 1 Mississippi each, if each one of the early swings was 1 second, tick, tock, then the later swings are still 1 second, tick, tock. In other words, even a realistic pendulum that seems to be damping down and slowing down in the real world is actually slowing down while it slows down. So it's not slowing down. It keeps time even as it loses space. The first person who first discovered this before doing all of this math, the first person who realized this with his eyes, conjecture, was Galileo, sitting in the Sistine Chapel looking at the chandeliers that are so long and so heavy on the bottom that they make for very good pendulums, still realistic, still real world, but very good ones. And he watched as they damped down and they're swinging, and he was like, wait a minute, it looks like those things are maintaining the same amount of time even as they lose amplitude. And then he tested it and tested it to the point where he was like, oh my God, they really are. Like, he didn't do math theory, he visually saw it and that's how real this is. And he was so convinced that harmonic oscillators maintain a constant frequency independent of amplitude, that then he went home and started making clocks out of these pendulums. There had not been steady, reliable mechanical clocks before this time. There were hourglasses, there were sundials, that's about it. He made clocks out of this discovery and then used the clocks to set up all the physics experiments with inclined planes and rolling balls and everything that you spend all of physics 203 learning. In other words, the physics that is our fundamental kinematics, the physics discoveries that were all made by Galileo in his lab on inclined planes and that constitute the entire first semester curriculum of physics, all of that was only possible because he had already done enough physics in his head to be able to make the clock that took the time measurements on which our knowledge of physics is built. I mean, that's pretty crazy, I think. I mean, and this is all from conjecture, then verified, and then built upon. I mean, he trusted his conjecture and then he tested it and he liked the results well enough to build more conjectures off of that. Okay. Oh, sorry, Stephen, question. Or do you just still have your hand up from before? Oh, okay. Okay. So, all right. Last thing I'm going to say, and then we're done for today. Actually, last thing I'm going to say is, okay, is I'm suddenly, everything we've been talking about has been mass on a spring, but I then keep sort of acting like pendulums are interchangeable with that. Like, because you did this, you've done at least one lab also on pendulums, and I keep sort of talking about them interchangeably. Why? Because for everything I said today was about these X equations of masses on springs, but it's all math, and the math doesn't care whether we call a variable X or Y or Q, as long as we know it's a dependent variable. So what I'm saying is, from here on in, okay, so and we have 3 minutes. We're going to end on this. I'm saying now, everything we just did was based on d2x dt squared equals negative k over mx. But all the math worked. We did the math. We found that the solution is, or a solution is x equals x naught cosine omega t. And from now on, let z, that's supposed to be a letter z there. Let z from now on, let Z from now on stand for any measurable dependent variable that you can imagine. Like Z could stand for position measured in meters, or it could stand for angular position, measured in radians, like as in for a pendulum. It could stand for temperature. It could stand for electrostatic field. Let Z stand for anything that you're measuring in time. Okay, then if that's true, and let omega squared be any constant. Like omega squared is not going to stand for a constant measured in radians squared per second squared. Okay, like omega squared is one. Like if omega is a constant, then omega squared is some constant, right? If omega squared as a lump now stands for any constant, then from now on, if d2z squared equals negative omega squared z, right? Then from now on, z oscillates harmonically at an angular frequency of omega, i.e. z equals z naught cosine omega t. What I mean is, and we're ending here, I'm saying from now on, in, oh yes, thank you very much. Thank you, Caroline. That's awesome. All right, I'll do it right when it's done. Thank you. I mean direct check for that. Okay. I'm saying from now on, if Z is anything, and say temperature, and you know for a fact that temperature can be described by this differential equation, d2z d squared equals negative omega squared Z. If omega squared is just any number, any constant, then the value of Z necessarily oscillates harmonically, necessarily goes back and forth at a frequency that's constant, independent of amplitude, and the frequency of the oscillation will necessarily be the square root of whatever that constant is. In other words, if you do the d2z dt squared equals negative 16z, then you know Z is oscillating harmonically with an angular frequency of 4. Like the angular frequency is always the square root of whatever that constant is in the differential equation. That's for anything for all time now. This is a big deal in PChem, by the way. All right, I'm going to go. We'll keep doing this. Just keep doing what you're doing in life. I'm going to post the thing right now. Thank you for reminding me. And then I have another class right now, so I am going to go. Oh, yes. Have a good day. Awesome. Thank you for being so patient.
Bye, Professor. Thank you.
Thank you very much. Awesome.
Have a good day, Professor.
Thank you. You too very much. Thank you very much. And yes, you too. Awesome. Okay. Thank you. Have a good day. Awesome. Okay.